Yeah, just take a long time. Or... People, I guess, the worst job that everyone's so scared. I guess it's, what the guy was trying to say, it's like he was doing all homework to try to. I guess that's what was going on. It was like you guys are thinking. So that was like, you're all set. I think there is a lot of those. Yes. Oh, wait, no, had this much. Basically, like adding. Now it's how it's just repeating. Yeah, titration. Yeah, depending on what's like. Yes. That's after today, we tried this. Yes. There was a couple like that. There was one last week. I guess I should have. Or like the lowest pH. Like that's what was supposed to do. Just go look at the same thing. It didn't. It just got off the grid. It gave me like it was just like see like I was just like it was I mean it's still that great. There's no one question I didn't do. I did all the other ones. So all that was that. It's the one. And probably also crazy. So I just wasn't recognizing the trend. So I didn't. I got to that point, I think if I switch those two equal sign, the best things. They usually hey, like I put us so much like wait, where do I go? Do I go by like trends or probably that's what I'm thinking about asking your question every time. I don't know.
So on this question, what was I supposed to do to, I understand how to recognize the trends that when something goes further this way or further down or further this way, more acidic on this side, more basic with this side. What should my thought process be on a question like this?
Send this to me, I will go through this.
Okay.
Oh, yeah, you gave me some point.
It's not going to. Yeah, because they should be adding this. Like, then you said, yeah, you know. And then- Or something. Right, concept is.
So this is the ultimate.
Oh, okay.
Okay, any questions before we get started? Okay, so if there's actually no questions, I guess we'll actually go back to the. What's the meaning of life? You can actually connect with me. Okay, once you actually get off this class. Okay. Okay, so on Tuesday's lecture, we actually start to introduce you the concept of titration. Okay, and I say for the midterm two, the most important thing that you should really know is that you need to know what kind of solution that you have, right? So I think that we need to actually emphasize this practice. That if I give you a solution, okay, can you actually figure out what kind of solution that you have? The other important thing that I think that you should get used to is that many students, when you actually read the questions, you can't get stuck. Okay, for example, okay, let's say you have this type of questions. That question usually a lot of these questions, right? What I want you to have is that, okay, once you read the questions, really identify what a species is. So let's look at this, okay? Calculate pH of a solution contain. This is actually the first species that comes up, right? And that's the second one. Okay, so I don't want you to just look at that. Okay, I want you to think about, okay, what is that species? There's only very few species we have talked so far, right? Basically, it's actually you have the strong acid, weak acid, acidic salt, strong base, weak base, basic salt. The second one is actually the buffer. This is all the solution you can have. Okay, so I'm going to translate all this chemical formula into those 7 solutions. Okay, for example, this one, okay, CH3COOA. Why is this kind of salt? So this is actually a basic salt, right? And then it's CH3COO minus, right? So you need to train yourself. So when you see the species, you know what you have. This will actually greatly help you to actually identify what kind of solution that you have. Okay, so when you see this, okay, I don't want you to say, okay, this is actually acetic acid, right? Instead, what I want you to have in mind is this is actually a weak acid. Okay, so weak acid, weak base, strong base. Those are the things that you need to actually keep repeating those concepts in your mind, so that when you encounter the questions, you can quickly identify what kind of solution that you have. All right. All right. So what we're going to do today is we want to actually go back to this titration concept again. Okay, so last time I did not actually finish this table, okay, but we're going to finish this table first. On Tuesday lectures, we say if your Tai-Yen is a strong base, okay, so this is actually Tai-Yen, okay. Your analyte can either be strong acid or weak acid, right? And then you have 4 different zones. Okay, so the zone number 1 is before titration. Zone number 2 is actually before your equivalence point. Zone number 3 is actually at equivalence point. Zone number 4 is actually beyond equivalence point. Okay, so those are the 4 zones. So if today your analyte is a strong acid, okay, so in the zone number 1, since you haven't added in any hydrate, the solution you are going to have will be a strong acid solution, right? Okay. You want to try, you need to actually try to answer all the things by yourself. Okay, because once you can answer all the things without any doubt, okay, then you pretty much know how to do when you encounter the questions. All right. How about the zone 2? What kind of solution are you going to have? Strong acid, okay. Zone 3, H2O, right? Because it's strong acid, strong base. They are going to interact completely. Therefore, all you have is just water, right? Zone number 4, strong base. Okay, so these are actually the things that you should have on the table. Okay. Second scenario, if today you have a weak acid to start with, okay, what's the solution you're going to have in zone 1? Weak acid, right? Zone 2. Sure, on here. Zone number 3. Zone number 4. Okay. You need to actually have a immediate response of all the things. Okay, if you can do that, you're pretty much all set. Okay. The reason why I say so is because do we know how to calculate the pH of a strong acid? We do, right? Because proton concentration will just simply equals to your strong acid concentration. Okay, so take negative log, you got your answer, right? Do we know how to calculate the pH of a weak acid? We do, right? Weak acid concentration times your Ka, take the square root of that, they give you a proton concentration. Take the negative log of the proton concentration, give you the pH. Okay, how to calculate pH of a buffer? HH equation, pH equals to pKa minus log acid over base. Right, so it's actually very straightforward, but the key is actually, can you recognize what kind of solution that you have? Okay, so how about a strong base? If you have a strong base solution, okay, as long as you have a basic solution, the first thing you calculate is actually your OH minus concentration, right? It's actually the opposite of the acidic solution, right? For the acidic solution, you start with proton concentration. For the basic solution, you start with the OH minus concentration, okay? It's called the symmetry, okay? So if you have a strong base solution, the OH minus concentration will simply equals to the strong base concentration, okay? And you take the negative log of that, you got your POH. 14 minus your POH will give you the pH. Okay, everybody follow the things? Okay, so if you don't, then let me know. I'm probably to actually write it down. Okay, so how about calculate the pH of a weak base solution? Its OH minus concentration is going to equals to square root of weak base concentration times your Ka or Kb. Kb, okay, make sure you know it is Kb, not Ka, right? Buffer is the same, right? HH equation. So those are the things that you need to know. Those are the things that you need to actually use to do all the calculations. Okay. Now let's do this part, okay? We did not actually tell you this part yet, okay? But you should be able to actually use the things you learn from the right column to guess what you're going to get in the left column, right? Start from this, okay? If you have a strong base as your analyte, okay? Your titrant is a strong acid, okay? What are you going to have in zone 1? Very good. Zone 2, very good. Zone 3, water, right? Zone 4. See, suddenly you guys can see these things, right? So you know what solution you have and you know how to actually calculate the pH. Okay, so things will become very easy for you now. Okay. How about this one? If you have a weak base to start with, okay, what are you going to have in zone 1? Weak base, right? Zone 2, buffer. Zone 3, weak acid. And zone 4. Okay, it is less simple. This table is the most difficult part of your midterm 2. Okay, but it seems like everybody can actually know, okay, what to fill in into the table. Okay, so it's very essential that you know what is your titrant, what is your analyte, right? And then you should know which zone you are at, because once you know which zone you are at, you know what kind of solution that you're going to have. Okay, once you know what kind of solution you are going to have, you know how to calculate the pH. Okay, so this is actually the most important part of this chapter. Okay. So what we're going to do today is actually we're going to apply this concept to do some more calculation. Okay, but we're going to start with the buffer first, okay, because I feel like most of the students still have problem with buffer. Okay, so we're going to do some buffer questions. Then we'll actually move to the titration questions. All right, you ready? Okay, so let's look at this. Determine the volume in mil. Oh, this is actually, I will go to this one later. Okay, I want to go through the buffer first. Maybe it's fine because it's actually all integrated, so it's okay, I guess. Okay, so let's do this first, okay. Determine the volume of species A, okay, HBr. Okay, like I say, when you see HBr, you need to know what it is, right? So what is HBr? Yes, that's something you need to actually always know, okay? Need to reach a half equivalence point in the titration of 44 ml of this concentration of NH3. What is your NH3? Octanol base. Strong or weak? Weak base. How do you know it's actually weak base? Yeah, I wish I would be actually on your side when you actually take your midterm. Okay, but I can't. Okay. So let's review this concept, okay? Periodic table is always your good friend, the best friend actually. Okay. So when are you going to have a strong base? Yeah, you must have the group 1, group 2 that associate with hydroxide or oxide. Okay, for example, lithium hydroxide, sodium hydroxide. Okay, once you see that, you know that's actually a strong base, right? Or you see magnesium oxide, calcium oxide. Okay, those are the two-way group, right? So you know these are the strong base. All other things will be weak base. Okay, so that's actually a very important concept that you should know. All right, so here you got these two things, right? And then he asks you these things called a half equivalence point. So half equivalence point is basically half of the volume of your equivalence point. Okay, so you need to actually figure out what your equivalence point first. Okay, so how do you figure out the equivalence point? So when you see equivalence point, the things that should pop up in your mind is actually that the mole of your titrant has to equal to mole of your analyte, right? So what is your titrant? What is your analyte in this case? Who will be the titrant? Who will be the analyte? HBI is actually your titrant, right? Why? How do we know that? Titrant can only be the strong acid or strong base. Oh. Right? Titrant can only be the strong acid or strong base. Therefore, your titrant will be HBI in this case, right? Therefore, the other one will be your analyte. Okay? So, how do you get the mole of your titrant? Will be the concentration of your titrant, okay, times your equivalence point, okay, which is going to equal the concentration of your analyte times the volume of your analyte. Concentration of your titrant. What is the concentration of your titrant from the question? Okay, 0.551. You want to know the equivalence point, right? Which is actually your VEP. Okay, the EP stands for the equivalence point. Okay, concentration of your analyte is 0.703. Volume is 44.37. Okay, so some student will say, okay, how come I can actually convert this one into liter, right? Because mole is actually the concentration in molarity times the volume in liters, right? So the things I do here is actually give you the millimoles, right? So yes, I can actually convert it to liter by dividing the number by 1,000, right? It is fine. Okay, then whatever number I got on the left-hand side, it will have a unit of liter, right? But since here I use milliliters, okay, so the volume I got on the left-hand side will have a unit of milliliters, but they are all fine. Okay. So your VEP is going to equals to 0.703 times 44.37 divided by 0.551. This is going to give you a number of 56.4. Okay, so has a unit of milliliters. Okay, but this is actually equivalence point, right? But the question is asking you the half equivalence point. Okay, therefore you know the half equivalence point will simply equals to your VEP divided by 2. Therefore you got 56.4 divided by 2. Therefore you got 28.2 milliliters. Okay. So to recap this question is that first, okay, the keyword here is actually the equivalence point, right? Once you see the equivalence point, it tells you it's actually that. It's actually some question related to the titration. Okay, so the first thing is actually want to identify who will be actually your titrant, who is actually your analyte, right? And that's actually why we will need to write this. HBI is strong acid. NH3 is actually weak base, right? And then you know for the titrant, it can only be strong acid or strong base. Therefore, you know your titrant is actually your HBI. Okay, the analyte will be actually your NH3. Okay, then you need to know the definition of equivalence point. Okay, definition of equivalence point is actually that the moles of your titrant equals the mole of your analyte. And the way you calculate the moles of the substance is using the concentration of that substance times its corresponding volume, right? The volume for your titrant will actually give you the information about the VEP. Okay, so then you collect the information from your questions, plug it in, then you can actually calculate the number of the VEP. But you also need to pay attention to the question. It is asking you the half equivalence point. Therefore, you need to actually divide the VEP by 2 to get the final correct answer. All right, so let's actually a logical flow to solve this problem. Okay, any questions? You can select, but you can also say, let's actually another hint telling you that the NH3 is a weak base, right? It can be a, I don't know how you're going to see it, okay, but those information is irrelevant to solve this problem. Okay. Any questions? Did I do anything wrong in the calculation? Okay, so that's actually the first question I want to go through today. Okay, let's look at this question again, okay? Calculate the pH at equivalence point. Okay, in the titration of this much volume, that much concentration of this species with that concentration of that species. Okay, so you have 2 species, right? You see the equivalence point, therefore you know it's a titration problem, right? Therefore, you need to actually identify who is actually your titrant, who is actually your analyte. Okay. You have one is actually HCl, which is a strong acid, right? What's this one? It's a weak base, right? You give it a Kp of less specific species, right? Therefore, you know the titrant is your HCl. The analyte is your morphine, okay, which is actually a weak base. It's actually a strong acid. Okay. So you want to calculate the pH at where? Equivalence point, right? Equivalence point is zone 3, right? Okay, so you know you want to know the pH at zone 3. Okay. What are you going to have at zone 3? If your analyte is a weak base, your titrant is a strong acid. We just went through the tables, right? Your titrant is a strong acid, right? Your analyte is a weak base, right? And then you know you're at zone 3, right? Therefore, you have a weak acid solution, right? So why it is a weak acid solution? It's because if you have a weak base, typically I roll BOH. Okay, weak base. You can use a BOH as a representation, right? You don't really care about what it is. Okay, but it's actually weak base. Strong acid, I typically write H+, right? And then when you have this, you know they have the same amount. They are going to consume each other completely, right? So all you have is H2O plus B plus. Okay, so the B plus will become a weak acid species, right? So how do you calculate the photon concentration of weak acid? You are going to use the B plus concentration times the Ka, right? This is actually what we have learned so far. Okay, if it's weak acid solution, you calculate photon concentration using your acid concentration times Ka at the square root of that. Okay, that's how you get the photon concentration. Okay, therefore you can calculate the pH using the negative log of your proton concentration. Okay, and that's actually what the question is actually asking for. Okay, so let's actually count the logical thinking you should have. Okay, everybody follow this? How do I know what? It's at zone 3, because in the question it says at equivalence point, right? So zone 1 is actually before titration. Zone 2 is before equivalence point. Zone 3 is at equivalence point. Zone 4 is actually beyond equivalence point. Okay, so in the questions, it says determine the pH at equivalence point, right? So that's actually zone 3. That's how I know it's actually at zone 3. Does that answer your question? Okay. So now, any other questions? Okay. So now it's actually, how do we actually figure out that B plus concentration, right? So that's actually the species that you will need to calculate the proton concentration. Okay. So here you are going to write this. I'm going to write for now, okay, but I want to actually practice enough that you can actually do all this operation in mind. Okay. So you have a BOH plus H plus. They give you H2O plus B plus. Okay. So in the beginning, you have certain amount of this, right? So for all the things, you want to calculate number of moles. Okay. So BOH, you have, that's the amine, right? So you have 0.116 times 30.77. You have that many millimoles of this species. Okay. For the protons, you have 0.231. Okay. Do you know how many more of that acid is? Not yet, right? Can you actually figure out? Okay. So because this is actually at equivalence points, right? So that we know the moles of your BOH is going to equal mole of your HCl, right? The mole of your BOH is 0.116 times 30 times 77. It's going to equals to 0.231 times your VEP, right? That's actually your equivalence point, the volume of your titrant at the equivalence point. So that you know your VEP is going to equals to 0.116 times 30.77 divided by 0.231. And then if you do the calculation, you should get a number of 15.45. Okay. So if you can actually follow along and you feel like you can actually do the calculation in real time, do it. Okay, so you can actually double check the things I write is actually indeed correct. Okay. So once you know that you know, you're going to have 15.45. Very much more of your strong acid, right? And they are going to consume completely, right? That means actually you are going to minus this much. You're going to minus that much. These two are actually the same number, right? And then at the same time, you're going to produce the many more of B plus. So the number should be, okay, so this, if you do this multiplication, okay, the number should be 0.0772. 0.0772, and you're going to produce 0.0772. Okay, so that once you reach equilibrium, you don't have any BOH, you don't have any H plus, right? All you have is 0.0772 B plus. Oh, sorry, not 0.72. who have calculator can actually calculate this for me because the 0.0772 is actually I divided by the final volume. So I got a concentration. 3.56895. Oh, that's actually a lot. Okay, 3.56 is fine. Okay, so you have 3. It's the same. They are the same, right? Because this equals to that. Yeah. So like in the end, you have 0.56 millimole of your weak acid B plus, right? But all you need to know is actually the B plus concentration. Okay, not number of mole. Therefore, you actually do one more step is that you need to divide the number of millimole by the total volume. Okay. Right now, the total volume will be 30.77 plus 15.45. Okay, so once you do the calculation, you got a concentration of 0.0772. Okay, so this is actually a part that you need to do some practice. Okay, because we are transitioning between moles and concentration. Okay, to calculate the total concentration of a weak acid, you need to know the molarity, the number of moles. Okay, and this is actually a part that you convert the moles into the concentration. Okay, so once you know this, okay, so this is actually your weak acid concentration. The next step you do is actually you can calculate the proton concentration using weak acid concentration times your Ka. Okay, so the weak acid concentration will be 0.0772. Ka is 1.6 times 10 to the negative 6. Once you do that calculation, you're going to get a value of 2.196 times 10 to the negative 5. Therefore, the pH is negative log of proton concentration, which is 2.196 times 10 to the negative 5. That's how you get the pH value is going to equals to 4.66. Oh, this is KB. Okay. Yes. Okay. This is Ka, right? But what was provided there is actually Kb. So you want to actually compute the Ka. So your Ka can be computed by Kw over your Kb. Kw is 10 to the negative 14. Your Kb is 1.6 times 10 to the negative 6. Therefore, you get your Ka equals to 6.25 times 10 to the negative 9. So you plug this in, it's 625 times 10 to the negative 9. And then you're going to get this value, and they will give you this pH. Okay, thanks for that reminder. Okay. Okay, so when we write things out, it looks super complicated, right? Because we have this ice table, so things actually become very occupy a lot of space. Okay, but if you actually practice enough, okay, this is actually how I would do it. Okay, because I know you are at equivalence point, right? Therefore, the first thing I will do is actually calculate your BEP. Okay, so I will still do this step first to get my BEP. Okay. And then the next thing I do is actually, because I know all your weak base will be consumed, right? Therefore, we're going to generate that much amount of the conjugated acid. Therefore, I know the moles I'm going to get for my weak acid is that much. Okay. Once I know that's actually the amount I'm going to get, I can just go from here to here. I know that is actually the number of mole of my weak acid. Okay. Then I need to recalculate the concentration. Therefore, I know I need to divide it by the total volume of the solution, which is actually a sum of the initial volume of your analyte plus the volume of your titrant, which is your BEP. Okay. Once I do that, I can get these things. I can get my weak acid concentration. Okay. Once I got my weak acid concentration, then things go back to this. Okay, then I can just follow along to get my final pH. Okay. With that being said, I can actually skip this part, right? I don't need to actually go through all this. Okay, but this takes practice. Okay, I'm so used to it, right? I can just think about these things in my mind. Okay, and that's actually what you want to achieve. Okay, because once you read the questions, okay, if you know this, you can just go straight to calculate the concentration of the weak acid. Okay, so when you start to do these questions in your homework, okay, trying to achieve this level of get familiar with all this solve process. Okay, it will actually greatly speed up the time that you need to solve this kind of questions. Okay, any questions for this? No? Okay, so let's look at the next one. A buffer contains 0.15 N of an acid HA, 0.27 N of its conjugated base A minus, has a pH of 4.83. What is the pH after 0.021 mole of NaOH are added into a 0.79 liter of the solution? Okay, so first is that you want to know what is actually the solution that you have, right? What do you have? What's the keyword here? Buffer, right? So when you see buffer, what do you write? HH equation, right? pH equals to pKa minus log acid over its conjugated base, right? Okay. Once you see buffer, write it out. Okay. Then read the question and fill in the information that you got. Okay. So you say you have 0.15 N of acid, 0.27 N of its conjugated base, has a pH of 4.83. Okay, so let's fill in this information. Do I have one pH? We do, right? So you can write 4.83 equals to, do I have my pKa? You don't, right? So just write down pKa minus log. Do I have my acid concentration? Which is 0.15, right? Do I have my base concentration? 0.27. Okay. So once you write out these things, what did you find? Yeah, so the first sentence is actually trying to tell you what? There's the things that they want you to know. They want you to know what the pKa is, right? Therefore, you can get your pKa is going to equals to 4.83 plus log 0.15 over 0.27, which is going to give you a value of 4.37. Okay, so let's actually the purpose of the first sentence. Okay, but the key is that if you see buffer, okay, and they give you a bunch of information, you should be able to see that the first sentence is trying to tell you what pKa is. Okay. All right. Now he asks you, what is the pH after you add in that much amount of a strong base, right? NaOH is a strong base. Okay. So what will a strong base do? So the strong base is going to consume. Okay, let's start from fresh. Okay, what do you have inside your solution? I know you have a buffer, right? Buffer is actually composed of weak acid and a conjugated base, right? A conjugated base of a weak acid is a weak base, right? So you have weak acid, weak base inside your container. Okay, now I'm going to throw in what? A strong base. So strong base will interact with which species? Weak acid. Okay, once the strong base interact with your weak acid, what does that produce? Okay, so let's write it down, okay? So in the beginning, inside your solution, you have HA and A minus, right? Okay. So if there you throw in what? NaOH, right? Which is OH minus. Okay. This is actually your weak acid. That's actually weak base, right? So what will that OH minus do? It's going to consume your weak acid, right? So what it does is this. Okay, so that OH minus is going to get a proton, right? Forming the water. Once they do that, it's going to produce A minus. Do you guys see this? It's very important you see this picture. Okay, inside the buffer solution, what you have is actually a weak acid and weak base. Okay, if you add in the base, it's going to interact with your acid and produce more of its conjugated base, right? So this is actually if you add in a strong base, right? Everybody follow this? Okay, now what happens if you add in HCl? HCl is a strong acid, right? So if you add in HCl, what we do? It's going to interact with your weak base. Okay, so okay, refresh. You have a buffer solution. You have a weak acid. You have weak base. Okay, inside your buffer solutions, right? So we just finished discussion about this. If in a strong base, it's going to interacting with your weak acid to produce more weak base. Okay. If you add in a strong acid into your buffer solution, okay, it's going to interact with who? It's going to interact with your weak base, right? And then the net result is that you're going to produce more weak acid. Okay, so that is the concept. Okay, you must know which species will be consumed, which species will be generated. Okay, so this is actually the very important concept for these type questions. Okay, so things right now, this is actually a specific condition that we have, right? You have a buffer solution, you're adding a strong base. Okay, so now you want to know, once you add in that much strong base, how would it actually affect the moles of your weak acid and weak base? Okay, what is the mole of weak acid that you have in the beginning? The way you calculate mole is actually you want to know the concentration multiply the volume, right? It says the volume of your solution is 0.79 liters, right? So you know your weak acid concentration is 0.15. The volume is 0.79. That's actually how many moles that you have, okay, for your weak acid. The weak base is 0.27 times 0.79. That's how many moles of weak base that you have in your buffer solution, right? So this is actually the initial. Right now you add in 0.021 mole of sodium hydroxide. Okay, so this one will consume your weak acid. Okay, and you want to know who is actually more, right? 0.15 times 0.279. Okay, what is this value? 0.1185. Okay, so you know this will be fully consumed, right? So you will actually consume 0.021, 0.021, and you plus 0.021 of your weak base. Okay. Therefore, once you reach equilibrium, what you're going to have will be 0.0975 for your weak acid. You don't have OH minus anymore, and you have 0.2343 for your base. Okay. So let's actually the moles that you're going to have for your weak acid and weak base after you add in less strong base. Okay. So once you do that, okay, you want to ask yourself again, what kind of solution do I have? What kind of solution do you have? What other species remaining inside your container is your weak acid, right? And then it's conjugated base. So you still have a buffer solution. Therefore, you need to use HH equation, right? So you know pH is going to equals to pKa minus log acid over base, right? Do you know your pKa? You do, right? So now you start to see why I need to give you the first sentence. Because I want to tell you what the pKa is, right? So this will equals to 4.37 minus log. Okay, so now you want to know what is actually a new concentration of your weak acid and then weak base, right? So to calculate concentration, it will be 0.0975 divided by 0.79 liter, right? That's actually a concentration of your weak acid. For your weak base will be 0.2343 over 0.79. Okay, so this will actually cancels out. Okay, so once you do that calculation, you're going to get a value of 4.94. Okay, so this will be the final answer for this question. Okay. Any questions? Okay, let's recap this type of questions again. Okay, so this type of questions again, you will see this it says buffer in the very beginning, right? Yeah, and then it say adding a strong acid or strong base. Okay, so in the first sentence, actually provide a clue that allow you to calculate your pKa, right? So if you see the buffer, you know you must use the HH equation, okay? And then once you write your equation and then we see all this information, you will realize what we want to tell you is actually you can calculate your pKa, right? And the next step is actually I'm going to add in some strong acid or strong base in my buffer solution, okay? So if you're adding a strong base, it's going to consume the weak acid in your buffer and produce more conjugated base. Okay. If you add in a strong acid, you will consume your weak base to produce more conjugated weak acid. Okay, so this is always called at equilibrium. Okay, so that you need to actually compute the new concentration of your weak acid and weak base. Okay, and you will know you are still going to have a buffer solution. Therefore, you still need to use the HH equation, right? So you use the pKa information from the first sentence, plug in the recalculated acid and base concentration, then you can just solve for your pH. Okay, so this is actually a very general logical flow to solve a question like this. Okay, but you need to actually have the ability to see that, okay, you have a buffer solution. Okay, and then you know when you're in either strong acid or strong base, how will it actually affect and calculate the new concentration for your weak acid and weak base. If you can do that, then you should not have any problem to solve the pH for this kind of solution. Is that clear? Okay, good. Okay, next question. The pH of 0.5 m acetic acid is 2.52. Calculate the change in pH when that much of this is added into that much of that. A lot of information, right? So what you do is that you actually read these things step by step. The first step, it tells you the pH of 0.5 m acetic acid is 2.52, right? So it says the pH equals to 2.52 for what is acetic acid? It is a strong acid, weak acid. Weak acid, okay? Weak acid. Okay, so you have 0.5 m weak acid. How do you calculate pH of a weak acid? So for the weak acid, we know this, right? And then right? So this is actually how we calculate the pH of a weak acid, right? So now it says pH is 2.52. Therefore, you know this is actually 2.52. Right? Therefore, you know the proton concentration of this weak acid is going to equals to 10 to the negative 2.52. Right? And then you also know the proton concentration equals to this, right? So equal to square root of weak acid concentration is 0.5 times your Ka, right? What this tells you is that the first sentence is actually a very unclear way to tell you what a Ka is. Okay. So you know your Ka will simply equals to 10 to the negative 2.52 square divided by 0.5, right? Therefore, you will get a number of 1.8 times 10 to the negative 5. Yeah, so these questions, okay, I put it here, right? But in your exam, he actually doesn't need to provide it. If it doesn't provide, then you do like calculation. I hope you do, right? Because actually the first sentence already tell you that. Okay, so if I write that Ka value over there, it makes things actually a lot easier. Okay, but if the chemistry department want to actually test your knowledge, right? They're going to erase those informations because they, you know that in the first part, he actually already give you that information. Okay. So now he want to ask you, calculate the change in pH when this species was into this solution. Okay, so now you want to actually start to translate this. Okay, CH3COONA. What is this? It is a salt. I know. What kind? Basic salt, right? So every time you see this Na, you want to actually remove it. So you have CH3COO minus, right? So you have this. You add into a CH3COOH. Okay. So now you add in a weak base into a weak acid, right? So you have a weak acid, weak base, and they are conjugated with each other, right? Because the difference between the two is actually just a proton. So you have a buffer solution, right? So how do we calculate pH of a buffer solution? HH equation, right? So pH equals to pKa negative log acid over base, right? And then pKa, you know, is negative log of your Ka. Ka is 1.8 times 10 to the negative 5. Okay, minus log. Okay, so you want to calculate the concentration of your acid, right? Acid concentration is 0.5. Okay. Conjugated base concentration is, it did not actually tell you the moles, right? But you can calculate it. It's 1.59 divided by 82.03. They give you the mole of your base. You need to further divide it by the volume, which is 49.9 divided by 1,000. Okay, so once you do the calculation, the first term will give you 4.7447 for your pKa. The second term will give you minus 0.1096. Okay, so when you do the calculation, you are going to get a value of 4.6351. Okay, so you know, once you do that, the pH is this value. But what the question is asking is actually calculate the change in pH, right? Change in pH means delta pH. Okay, so in the beginning, the pH is 2.52, right? And then once you add in that conjugated salt, the pH becomes 4.6351. Therefore, your delta pH will simply equals to 4.6351 minus 2.52, which is going to give you an answer of 2.12. Okay, so this is actually how you solve this type of questions. Any questions? Okay, so if not, that is actually how you where?
That like on the bottom, is that okay? I see.
Yeah, so this is mole, this is volume, right? So let this give you the concentration. Mhm. Okay. So any other questions for this? Okay, so if not, then this is actually the question about the indicator, right? So on our YouTube videos, right, I tell you how to actually memorize a few indicators. Okay, so we have this this chart. I think is actually useful, and then I also provided you that these are the 3 terms that you want to actually memorize. Okay, so I guess you will need to actually go through the YouTube video to understand what all those terms means. Okay, but apply those terminology will help you to really understand what indicators that you need to use. Okay, the most important thing is actually all those terminologies actually based on what kind of analyte you have. Okay, so if you have a analyte is a weak base, then the methyl orange and methyl red will be the most commonly used indicator. Okay. If you have a strong acid, strong base as your analyte, okay, where I actually use S as a representation, okay, then the bromethyl blue or the phenol red will be the commonly used indicator, okay. And if you have a weak acid as your analyte, then you have a phenolphthalein and then the alizarin yellow as your indicator. Okay, so these are the commonly used indicators you are going to see. Okay, but when you do your homework, okay, they will ask you to actually check out the tables. Okay, then you just need to figure out, okay, what is the range, what is the pH range they're going to have changed that fit into your pH at the equivalence point. Okay, so that's actually not too much that I need to explain here. So do watch the YouTube video so you know how to use those informations. Okay. So I want to use the remaining couple of minutes to go through something I feel like I didn't actually make it super clear last time. Okay. So I also like many of you should actually see these questions already. Okay, so the question says, determine the Kb of certain species in a 0.2N solution that this base is certain percent ionized. Okay, so I guess this ionized and unionized, these things actually bothers many of you. Okay, so I want to actually re-emphasize these things again so that you can see these things more clearly. Okay. So here you know the species that you have is CHO2 minus. Okay, so CHO2 minus. Here I feel like you need some fundamental chemistry knowledge. Okay. So you need to see that this is a conjugated base of CH2O2. Okay. Structure-wise, this is actually what it looks like. Okay, so these are the two species where this one is actually the acid. This is actually the conjugated base. Okay. So you should see these things is a monopodic acid, means actually it can actually dissociate once. Okay, so this dissociate into that and then give out H plus. Okay, and this one cannot give another proton anymore. Okay, So you want to know the KB of this guy. Okay, so CHO2 minus, when you store this things inside the water solution, okay, it serves as a base, right? So it's going to capture the protons so that you get CH2O2. You can't doing the things backwards. All right. And this is actually the part that the ionized matter. Okay. This is actually your weak base. Okay. Once you interact with a proton, it becomes unionized. Okay. So it's really depending on what species that you have here. Okay. And then it's a base, right? So it's going to capture a proton to generate its conjugated acid. Okay. So it says you have that much percent ionized. If you look at these three species, which species is actually the species that is ionized? You have species 1, species 2, species 3. Which one is actually ionized? Species 3, right? That's actually the one doesn't carry a charge, right? So what it says is actually the base is that much unionized. Okay, so how to actually translate into this equation? No, this is actually the percent dissociation, right? Because it actually tells you this sort of like, okay, how much you actually go to the right-hand side, right? So the percent dissociation previously defined is actually the product over your initial species, right? So this means the percent dissociation will be the CH2O2 over your CHO2 minus. Okay. So this is actually a part that is very confusing, I know, but I guess the syn gauge trying to actually play some, I don't know, they use this very weird terminology to confuse everybody. Okay, so let you know, this thing is actually 0.014% ionized. Okay, that means actually, if you do that, that will be just equals to 0.0014%. Okay. Of course, here I wrote this way, right? Another way to write this is that CHO2 minus plus H2O. That's going to produce OH minus plus CH2O2. Okay, so the second equation I write is actually equivalent to the first one. Okay, but I guess this will make more sense because the things that you have is a weak base, right? So you expect you are going to produce OH minus on the right-hand side. Okay. So once you do that, then you can go back to the percent dissociation concept, where it's actually the OH minus concentration over your initial base concentration. Okay. So in that case, you know, here I can write this, right? This and that is going to have the same amount, because once you interact with this, all this actually 1-to-1 ratio, right? So the OH minus concentration is going to equal to your CH2O2 concentration. So this is actually indeed equals to your percent dissociation. Okay, and then the percent dissociation will give you that the OH minus concentration is going to equals to 0.0014% times your CHO2 minus concentration. In this case, is equals to 0.28. Okay, and then you know this is actually a weak acid solution. Therefore, it's going to equal the square root of weak base concentration 0.28 as your Kb. Then you solve this equation to get your Kb. Okay, so this is actually a very confusing questions, I have to admit. Okay, these things can have another way to ask you. Okay, it's that. Okay, come back a little bit. Okay, so the reason it's confusing is because the species that you have in the beginning, it is ionic species. Okay, so it's sort of like once you interact with water, you generate your OH minus, then this one become unionized. Okay, the reason I say this question require you have to have some chemical knowledge is that you need to write the correct equation to know who is actually ionized, who is not, so that you can actually make the proper judgment for the percent dissociation. Okay, this question can be modified. Like if I say today I have a base NH3, okay, and then in a 0.28 n of this solution, it got that much percent ionized. Okay, if that is the new question I ask, then the things you should have in mind is, okay, my NH3 is going to interact with my H2O. So that is going to produce H plus and then NH4. So OH minus plus NH4 plus. Okay. So now if I say the NH3 has 0.0114% ionized, okay, then what it tells you is that the OH minus concentration over your NH3 is equal to 0.0014%, right? Because right now all your product is ionic species. Okay, so this is actually what it translates to. Okay, but if I say this base is 0.0014% unionized, okay, then what it translates to is actually your NH4 plus and then your OH minus will equals to 0.9986%. Okay, so it's actually very confusing questions. Okay, but I want to actually go back and think about it. Okay, so if you feel like you still don't get it, then probably we should actually come again. Okay, so watch the videos. Okay. All right, so using the very last few minutes, okay, I'm going to go through a few questions to just let you know what are the things you need to practice. So you can actually really do well for the midterm too. Okay, I'm just going to read through the questions. I'm going to ask you a lot. Okay, is this weak acid, strong acid, or buffer? Okay, so give me the information. Calculate pH of a solution prepared by adding that much of HCl into 80 ml of buffer that is comprised of lead and lead. This is actually a question that, like the one we actually went through in question number 5. Okay, so again, is you have a buffer solution. You add in a little bit strong base or strong acid, right? that is actually telling you need to actually recalculate the new concentration of your weak acid and weak base, and then use HH equation to compute the new pH. Okay, so that is the things that you want to see in these type of questions. Okay, so it's going to be actually a very standard way to ask it, right? You just need to actually get used to it. That you should know what solution that you have. Okay. Okay, for this, what is this? Weak base. Okay, so you have a weak base solution. You mix with hydrochloric acid. So what is this? Strong acid. So you know your analyte is your weak base. Your titrant is your strong acid, right? All you need to do is actually figure out which zone you are, right? Once you know the zone, then you know what kind of solution that you have. Then you can calculate the pH. Okay, so next questions. Okay, you have this and that. What kind of solution do you have? A buffer solution, right? Because this is actually a weak base salt, right? This is actually a weak acid. So you have a buffer, right? So HH equation. Okay. So you start to see that if you know what solution that you have, calculation is actually very straightforward. So all you need to really practice is actually, when I read the questions, can I just know what solution that I have? If I do, solution should be actually straightforward. Okay. The very last one. Okay. What's this? What kind of salt? Acidic salt, right? So weak acid solution. How do we calculate weak acid solution? Proton concentration equals square root of weak acid concentration times Ka, right? Negative log of that proton concentration give you the pH. Do you have the Ka? You don't, right? So Ka equals Kw divided by Kb. Then you can solve these questions. Okay. So now I hope you start to see that, okay, if you can 100% sure what kind of solution that you have, you will actually be 100% sure what equation to use, right? And then just to figure out, okay, can I get those information from the questions? Okay, you want to do this really quickly. Then if you can do those things, then you will be totally fine for your midterm too. Okay, so that's all for this. Okay, and then I know you guys are going to have a great time for your spring break. Okay, but when you come back, okay, we are going to spend one lecture to finish up the